Hi folks, in this video we are going to learn how Bayes theorem can be used to do machine learning. So this is of course going to be a very simple method that we are going to see, and we'll see more complicated methods in the future, but despite the method that we are going to learn in this video being very simple, but it is still very powerful, so simple does not mean bad. Simple can be very profound also. So the method that we are going to learn in this video is called the naive Bayes algorithm. So why naive Bayes? Bayes comes from Bayes theorem. So because we are going to use Bayes theorem over here, the word Bayes is there. But what does the word naive mean? So some people translate it as being idiotic, and in some references you may also find the phrase idiot Bayes being mentioned. But I definitely strongly disagree with that definition. Naive does not mean idiot, naive means simple, or in Hindi, for example, you may translate naive as bewakoof, but I would, again disagree, and I would say naive to be bhola bhala or a simpleton. So it is called naive because of a reason that we are going to see in the video. But basically, it is called naive because it is a very simple application of Bayes theorem. And what is the simplicity is what we are going to see as we unfold more details of this naive Bayes algorithm. So once again, naive is not idiot. It is just a simple application of Bayes theorem. So again, let's take a very simple example of classification that we may want to do. As you all know, one of the most powerful uses of machine learning is in email classification into normal and spam messages. Earlier, till a few years back, a lot of spam email used to come into our inbox, and a lot of good emails used to go into our spam folder. But now more or less the problem has been solved, and Google and other email services have found an algorithm to almost perfectly, I would not say perfect because still some misclassifications do happen, but almost perfect way to classify incoming email into spam and normal. So of course we are not going to go into all those complicated algorithms, but we will see a simple way in which Bayes theorem can be used to do this email classification. So we are going to classify our emails into two categories. One is normal and the other is spam. So we denote this spam by S and we denote this normal by N. So what are we going to use to do this classification? What we are going to use are the words in the email that we get, and that is why this method is also called a bag of words model or a bag of words method. So when you get email in a particular language, it can be English, Hindi, or any other language. It basically consists of words which are arranged to form sentences. Okay, and the way a sentence is formed is very non-trivial. So any random collection of words does not form a meaningful sentence. So there is a particular order, there is a particular grammar to it, but that we are going to ignore for the time being, and that is why this is called a bag of words model, because we are only going to consider the word occurrences or the word frequencies and totally ignore all the other complications that arise when we study languages. So now let's say our bag of words of course has many words. English vocabulary of any other language is very vast. So without getting into all those complications, let's say that we focus on only 6 words. What those words are is again not very important, but let's say there are these 6 words which we are going to use to do our classification problem. So what we are going to do? We are going to see whether a certain word is present in our incoming email or not, and using that we are going to classify our email into normal and into spam. And here for doing this classification we are going to use Bayes theorem. So now in order to do this classification we need what is called training samples or training data. So what is training data? Training data is a collection of emails which is already labeled as normal or spam. Okay, so that we know, our algorithm knows that what it is that constitutes a normal email and what is it that constitutes a spam email. Because if we don't even know about it, then how is it that we are going to do this classification? And that is why this training data is extremely important in most of machine learning, I would say. Not all of machine learning, because there are some kinds of machine learning where the concept of training data does not apply, which we are going to see in later videos. But in most of machine learning, we need some kind of training data to train our algorithm to learn how to do various classification tasks. So let's say we have some such training data of some size. We don't care about the size right now. We just know that it is large enough. So this training data contains a lot of emails which are normal, and it also contains a lot of emails which are spam. So now let's say that our training data has, let's say, 70% normal emails and 30% spam emails. Okay, just for the sake of statistics. Okay, these numbers are not sacrosanct, but just to show you how these calculations are actually done. So now what we do is that we take all the normal emails and we count how many times each of these words W1, W2, W3, W4, W5 and W6 occur, and we divide that by the total number of words, and from there we get the probability that I have a word W1 given that my email is normal. Similarly, I can compute probability of word 2 given that my email is normal, probability of word 3 given my email is normal, probability of word 4 given my email is normal, probability of word 5 given my email is normal, and lastly probability of word 6 given my email is normal. So all these numbers I can calculate very easily using a simple Python program. Similarly, I can also find probability of the same word but given that my email is now spam. Probability of word 2 given S, probability of word 3 given S, probability of word 4 given S, probability of word 5 given S, and finally probability of word 6 given S. Okay, so once again what did we do? We took all the normal emails and we counted how many times W1, W2, W3 and so on occur in normal emails, and we divided by the total number of words of the normal email. Similarly, we did that with the spam emails also. We found out how many times W1 occurs, how many times W2 occurs and so on, and we divided that by the total number of words and we got these probabilities. So let's just fill up some numbers in order to do the calculation. So these numbers do not necessarily represent the reality, they are just some numbers that I picked up just like that. Okay, so don't take these numbers very seriously, they are just a figment of my imagination. 0.8 and 0.12, and then here let's say we have 0.11, 0.04, 0.14, 0.31, 0.21 and 0.19. So these are the 12 probability values that we have, which we have calculated from our training data. Okay. So now, after having trained our naive Bayes model, we have another email which just landed up in our server. And the server's job is to classify that as normal or spam and then send it to the appropriate folder. So what do we do? In the incoming email, we find out which of these words are present. Okay. So we will see what happens when you also take the count of those words into account, but for the time being, for the sake of simplicity, let us ignore that for a while. So what we just bothered about right now is which of these 6 words are present in my incoming email. So let's say I have a incoming email which has the words W3, W5 and W6, and it does not have the other words. So W1, W2, W4 are not present in my incoming email. And now my job is to classify this incoming email as spam or normal by using this naive Bayes classifier. So what do I do? What I do is to calculate two different probabilities. So what I do is that I calculate the probability that my email is normal given that I have W3 and W5 and W6 in my email, and I also find out the probability that my email is spam given that I have W3 and W5 and W6 in my email. And then what do? I will classify it as normal if this probability is greater than this probability, and I will classify it as spam if this probability is greater than this probability. As simple as that. So now let's see how we can calculate these probabilities by using the data that we have from our training set. Okay. So here is where we will use our awesome Bayes theorem. So this probability is given as, by using Bayes theorem, probability of W3 and W5 and W6 given that my email was normal divided by probability of W3 and W5 and W6. Okay, so this is just a simple application of Bayes theorem, and obviously I also have to multiply probability of n over here. Similarly, this is equal to probability of W3 and W5, 6, given the email is spam, multiplied by the probability that the email is spam, divided by probability of W3 intersection W5 intersection W6. So now, as I told you, all that we care about is which of these two quantities is larger. Okay, so we are not interested in the actual values of these quantities, but only in checking out that which of these is larger. And so this denominator is of no consequence to us because it is exactly the same on the both sides. So what do is that we remove the denominator, and instead of the equal to sign, what we have are the proportional signs. So the probability that we wish to calculate is proportional to this value, and this probability is proportional to this value, because all that we wish to do is a comparison between the two. Okay, so good so far. So how do we calculate this probability? So what we have over here are the individual word probabilities. Okay. From there, we want to find out this composite probability. So here we make the most crucial assumption that makes it the naive Bayes classifier. So the word naive or simplistic comes from the assumption that we are going to make now, which is that these words are independent of each other in their occurrence in the email, meaning that the occurrence of these words has nothing to do with each other. Whether W3 is coming in the email or not has no relation whatsoever to whether W5 and W6 or any other word is also coming in. So this is the assumption of independence, which frankly speaking is not strictly true in any linguistic text because there are very significant dependencies. But as it turns out that despite this assumption not being strictly true, it still gives us a very, very good accuracy of email classification. And that is why this bag of words model is still used for many, many problems despite the underlying assumption of independence not being true. So this is kind of a weird thing in machine learning, or I would say in many topics in science, that although the models we use, they make assumptions which don't truly reflect the underlying reality, but still the models are found to work very well in practice. That's a mystery and hope somebody figures it out someday. So what we are going to do is assume independence. So under this assumption, what we can write is that this probability is proportional to probability of W3 given n into probability of W5 given n into probability of W6 given n into probability of n. Similarly, this is proportional to probability of W3 given S, probability of W5 given S into probability of W6 given S into probability of S. And now, lo and behold, we have all these numbers available with us, which are there in the table over here. So just take these values and these values. So this is P of n 0.7, P of S is 0.3, and just plug in over here, and what you will get is 0.0012768, and here what you will get is 0.0016758. Okay, amazing. So now that you see that this number is larger than this number, so finally our incoming email has been classified as spam. So this simple naive Bayes classifier has told us that our incoming email was spam. So here, as you know, we have made two very crucial assumptions. The first assumption is that of independence, that we wrote these probability as a product of these probabilities. That was the first or one of the assumptions. The second assumption, which is also a very important assumption, is that we have just noticed whether a word is present in the email or not. We are not worrying about the count of the particular word. We are only worrying about the occurrence of the word, that whether it is present or not. What if we wanted to make it slightly more complicated and wanted to worry about how many times a particular word is occurring in the email? That is actually again very, very simple to incorporate. Independence cannot be violated so easily. That requires a more complicated model. But keeping independence intact, we can incorporate the number of times a word occurs very, very easily. So let's say the word 3 occurs some n3 times, word 5 occurs n5 times, and the word 6 occurs n6 times. So there is a very simple way of modifying this method, and what we do is just raise all these probabilities by the suitable power of the number. So this also goes as n3, this goes as n5, and this goes as n6. So now this updated model is taking care of the number of times a word is occurring in your incoming email. So remember that we are still assuming independence, and that is why this method is still naive based, but this has gotten little more advanced, if I may say so, where the number of words are now being taken into consideration. So a simple example of what difference this would make. So let's say our n5 and n6 are still equal to 1, but n3 is equal to 2. What that means is that w3 is occurring twice in my incoming email, and w5 and w6 are occurring only once. So now if you do this calculation once again, what you will find is that this email will now be classified to be as a normal email instead of a spam email. So taking into consideration the number of times a word occurs in the email can significantly change your prediction. So the previous method, where we did not consider the word occurrences for our calculation, is what is called the Bernoulli naive Bayes method, because there we were only checking the presence or absence of a word. But if you now start considering the number of times a word occurs in your email, that becomes the multinomial naive Bayes method, and both of these can be very easily implemented in Python. So once again, so this method is called naive Bayes because it is based on Bayes theorem, and it is called naive because it is a very simple implementation of Bayes theorem, and the simplicity is because we are assuming independence of these different words or these different methods or these different events. So now one more thing that you would have noticed is that this formulation of the naive Bayes algorithm assumes that your features or your data is discrete in nature, meaning that in the Bernoulli case, whether your word is present or absent, meaning 1 or 0, or in the multinomial case also, you have a discrete set of integers which represents the number of times the word occurs in your incoming email. But what if the features did not take discrete values but instead took real values? So, for example, let's say you have a group of people and you want to classify them using their height, weight, and let's say some other kinds of measurements. So, of course, strictly speaking, all measurements are again discrete in nature because any physical instrument has a finite resolution and a finite precision. So, you cannot ever actually measure any real number. So, any measurement is a set of finite values. But when the possibilities become very, very large, there it makes sense to model them as real numbers instead of as discrete values. So in that case, we have to use what is called Gaussian naive Bayes. So we will again not get into too much details of the method. So let's say you have some set of data which you want to classify into two categories, C1 and C2. And for doing this, you have, let's say, n different features or parameters, which we are going to denote by x1, x2, x3, and so on up to xn. So now each of these xi's take real values. They are no longer discrete. And so in order to apply your Bayes theorem, you need to calculate the probability of x1 given c1 and the probability of x1 given c2, and you have to do this for all the other x2, x3, and so on. So now earlier for the discrete case, we could do this just using frequency counts, but that is not possible now because these xi's take real value, so these probabilities would actually be 0. So instead of worrying about these probabilities, what we do is that we model this as distribution functions. So we say that what is the probability distribution function of x1 given c1 and x1 given c2, similarly for other x2, x3, and so on. And what we do is that we model this and this as Gaussians. So now we know that the Gaussian distribution is defined by two parameters, the mean and the variance. So if you know the mean and the variance of the Gaussian distribution, you can write an explicit mathematical definition, a mathematical expression for the distribution. So what we do is that we take all the training data which belongs to C1 and we find the mean and the variance of the parameter x1, and using that we define f as a Gaussian with those two parameters. Similarly, we take all the training data which is in class C2, we find the mean and the variance for the parameter x1, and using that we define this as a Gaussian using those two parameters. So here again it is important to note that these actual distributions may not be Gaussians, but we use a Gaussian distribution for the sake of simplicity. A more accurate method would be to actually estimate the expression for these distributions, but that is a fairly complicated process. So for the sake of simplicity, and it surprisingly works very well in practice, we assume these distributions to be Gaussians with a certain mean and variance. And the real test of the accuracy is to actually apply it to a testing data and see whether it works or not. So if you take this model, apply it to a testing data, do all other kinds of accuracy tests, and if you find that the accuracy is high enough, then great, you can be happy with it. But if not, then you have to again come back, work around and see what other changes you can do to improve your model. So this was a very simple introduction to this very simple and beautiful algorithm called Naive-Bayes algorithm. In the future, we are going to see some more advanced methods which again use Bayes theorem but are slightly more complicated, where they do not assume this independence of the various features. So before closing, let me just mention that there is something called the Bayes optimal classifier. So this Bayes optimal classifier is kind of a perfect classifier which does not use any kinds of assumptions of independence or any other such simplistic assumptions, and because of that it is very, very difficult to implement in practice. But theoretically speaking, this concept very much exists, and there is one way of implementing it in practice which is reasonably good enough by what is called Bayesian belief networks, which we are going to see in the future in this course. So till then, stay connected.